Good morning students. Today we can do one problem based on Boussinesq equation. Before that I am going to summarize our previous lecture. Okay. So we were discussing about the stresses on a soil mass due to a constant load. So in order to find out the vertical stress due to a constant load, there are mainly two methods. First one Boussinesq equation, second one Westergaard's formula. But in your syllabus only Boussinesq equation is there. So what is the equation for finding out vertical stress due to a constant load by Boussinesq theory? So the equation is like that, that is the vertical stress at any point A due to a constant load P is equal to 3p by 2 pi z square 1 by 1 plus r by z the whole square raised to 5 by 2, where r is the radial distance of that point from the vertical load and z is the depth of that point from ground level. Okay, so here this is r and this is z, and if the point where we are finding out the vertical stress is directly below the load, that is if the point A is somewhere here, what will be the value of r? In that case r will be equal to 0. So if we are finding out the vertical stress which is directly below the point load, the value of r will be equal to 0. Otherwise there will be some value for r. Okay, so r is the radial distance, z is the depth, and we have discussed about influence factor IB. So in this equation the constant is replaced by this influence factor IB. So equation for vertical stress is P by z square into IB, where IB is equal to 3 by 2 pi into 1 by 1 plus r by z the whole square raised to 5 by 2. So by substituting values for r and z, we will get IB. We will get the value of IB from this equation. So there is a table indicating the variation of influence factor with r by z. You need not study all these values. You just understand there is a table which shows the variation of IB and r by z. So by referring this table, we can get the values for different areas. From this, using this chart, we have drawn the pressure distribution diagram, that is distribution on horizontal plane, distribution on vertical plane, and isobar. Okay, so today's problem, this is the problem. A point load of 600 kilonewton act at the surface of an infinite half space. Determine the vertical stress at a depth of 5 meter directly below the load and at a radial distance of 4 meter using Boussinesq equation. So here the question contains two parts. In first part we have to determine the vertical stress at a depth of 5 meter which is directly below the load, and in the second case we have to find out the vertical stress at a depth 5 meter and at a radial distance of 4 meter. That is, in case 1 depth is z is 5 meter and r is 0 because directly below the load. Okay, in second case the point is somewhere here, point is directly below the load, so in that case r will be equal to 0. In the second case r is 4 meter, radial distance of 4 meter. So first you write down the equation, Boussinesq equation, that is sigma z is equal to 3q by 2 pi z square 1 by 1 plus r by z the whole square raised to 5 by 2. So case 1, q is equal to 600, point load is 600 kilonewton given, z is 5 meter and r is 0. Since the load is directly since the point is directly below the load, r is equal to 0. So substituting these values we will get vertical stress as 11.46 kilonewton per meter square, and in case 2 the radial distance is 4 meter, so other values are same, so it's the same problem. So r is equal to 4 meter and substitute these values and we will get vertical stress as 3.325 kilonewton per meter square. Okay, so this type of problem is usually asked for university question. So first you should thorough about this Boussinesq equation. Problem is very simple, direct substitution. So next problem, compute the stress at the center of an edge of a footing 1 meter by 1 meter and compare it with below the center. Given the footing is subject to a total load of 200 kilonewton uniformly distributed over the footing. However, for computation purpose, you may assume the total load of 200 kilonewton as a point load acting at the center of the footing. The depth for comparison may be taken as 2 meter. Also sketch the stress variation at 2 meter depth. So here there is a footing 1 meter 1 meter by 1 meter dimension, and at the center here there is a load of 200 kilonewton which is uniformly distributed, and they also given that we can assume the total load of 200 kilonewton as a point load acting at the center. We can take 200 kilonewton as a point load acting at the center. Okay. So first you write down the Boussinesq equation. In second case, at the center of the footing, what is Q? 200 kilonewton, and at the center what will be R? R will be equal to 0, and Z is depth. Depth is given as 2 meter. Okay, since we are calculating the load at the center, R is equal to 0, because we have to sketch the stress variation. So first we have to find out the stress at center, and we have to find out the stress at the edges. Okay, so we have to find out the stress at center and stress at edge. So first we are calculating stress at the center. So for that, R is equal to 0, and substituting these values we will get 23.87 kilonewton per meter square. And in the second case, we have to find out the stress at the edge, at the center of an edge of the footing. Okay, center of edge of the footing. Q is equal to 200, and R, what will be R at the edge? This is the so the dimension of footing is given as 1 meter by 1 meter. So from center to edge the distance is 0.5. So radial distance 0.5, that is R is equal to 0.5 meter. Then depth Z is equal to 2 meter, and substituting these values we will get 20.51 kilonewton per meter square as the stress at the edges. Okay. Okay, so we can since in the question it's asked to sketch the stress variation. So the variation will be like that. At the center the stress will be maximum. Okay, so towards the edges the stresses will be decreasing, and at the edge the value is 20.51. Okay, so this is the problem based on Boussinesq equation. Some other problem I will give as your first assignment. Okay. Today's lecture is over. Thank you.